So we're first going to look at something called virtual process topologies in MPI, and then we'll see something called neighborhood collectives that takes advantage of these process topologies. So the basic idea in this process topologies is fairly simple. And the idea is that your application that is decomposed among a set of processes has some kind of communication pattern in it. And some process, each process is communicating with some other set of processes, and maybe not with others at all. So the communication is between one rank and a set of other ranks, and so on for all other ranks. So this defines your communication pattern. And so if these processes that are communicating frequently are located when the job is launched or even at runtime, if they are located nearby somewhere, what nearby means, it depends, but let's say most of them are on the same node or they are nearest neighbors in that in the torus or mesh or whatever, then your performance is likely to be better because all the communication is nearby on the fast links or on the same node or so forth. Whereas if you don't have this information about who is communicating with whom, by default, the resource manager or whatever it is that launches your job is just going to launch it in some default manner, which would be start with rank 0 and then just go on assigning rank 1, 2, 3, 4 in some straightforward order. So if you're, say, running on a cluster, typically it would and if you have many cores on each node, it would launch the job with, say, rank 0, 1, 2, 3 on node 0, and then 4, 5, 6, 7 on the next one, and then 8, 9, 10, 11 on the other. So that's just the default order. That may not be the best order for your application's communication pattern, right? Let's say rank 0 communicates a lot with rank 5. So it would make sense that they are both located on the same node. So this kind of mapping or launching a job so that communicating processes are located nearby is what all this is about. So there are two ways to do this. One is, let's say you know beforehand itself what this communication pattern of your program is. And how would you know it? One is because you've written the program, you understand your problem, and you know that, let's say you have a 2D stencil or a 3D stencil, then all the communication is nearest neighbor. So you know the communication pattern. If you have a more unstructured code, you could do some profiling beforehand to know what the communication graph looks like. So in some way you might know. So one way is at the job launch time itself, you could provide this information to the scheduler or the resource manager saying, hey, this is how the communication pattern is. So then launch these processes in a way so that the communication is efficient. It turns out that method is not widely supported, or if it is supported, it's supported with some limitations, and it's not the most general way of doing it. So in the example I gave where you're launching jobs on a cluster, you might have some options like instead of 0, 1, 2, 3 on the same node, it will launch 0, 1, 2, 3 on different nodes and then start round robining, or a few simple variations of these patterns. You don't have a more a complex way of doing that. So that's one way. That's what this slide says, and you may or may not be able to use it. So the other way, which is what I'm going to talk about, is something that you can do within your MPI program after it starts, and using some functions that MPI provides, and that is what is called virtual process topologies. So the basic idea here is as follows. When you launch your job, you start with an MPI COM world, right? And that might just be the default ordering that the system provides for you. That might be just the simple 0, 1, 2, 3 in a round robin manner. So you'll have a rank 0 in COM world, rank 1 in COM world, rank 2 in COM world, and so forth. Now, after that, as soon as you get your job is launched, at the very first thing you could do is call one of these topology functions in MPI, which one of them is a Cartesian topology, another is a graph topology, where you indicate that in the Cartesian case that you are going to do a stencil computation, be it 2D or 3D. You can have any number of dimensions, and what is the number of processes in your logical decomposition, or the 2D mesh case, and you call this function, and what it returns to you is a new communicator, right, in which the processes may be reordered. And by that I mean what was rank 0 in COM world might get a different rank in this new communicator. The idea being that with this, after this reordering, because you have specified the communication pattern, the MPI implementation has now assigned new ranks to these processes so that the communicating neighbors are located nearby somehow. Does this make sense? So what you're left with now is two communicators. One is the COM world that you got, you had anyway, and right before doing anything else, you've also called this function and specified your communication pattern as a Cartesian or a graph, and we'll see how to do that, and which returns to you another communicator in which processes, the same processes, may have a different rank. So nothing has changed, or processes have not moved around, or nothing has really happened. The same processes now have two different ranks. One is the rank in COM world that they always had, and if you had not done any of this topology stuff, you would have just used that rank. But there is this new communicator that you've gotten as a result of specifying the topology, in which potentially processes may have different ranks. And now what you can do is ignore the COM world. You don't use the COM world at all. Start using this new communicator as your communicator, and you have now a new rank in this communicator, and these ranks are such that the communicating neighbors are located somewhere nearby. And from then on, your program will function in a way that the communicating processes are nearest neighbor. And the reason I say that you do it right in the beginning of your program is that since you have not done anything else, you have not done any computation, you don't need to move data around, or you don't need to do any remapping. You're starting your program effectively with a different set of ranks. And so then on, you don't need to do anything special. Is this clear? Because this is the basic idea, and how, what functions you need to call, and that which we are going to see, that is just detail. But I find that this basic idea often is where people get a little stuck. Yeah.
What if you don't know which process is going to communicate with which process? I mean, unless you read your data. And I'm coming from an unstructured mesh point of view, where your mesh, once you read your mesh.
Yeah, then you know. So that is a more irregular pattern. So maybe you can, so there you have two choices. If you can do it in the second run of the code. So if a mesh doesn't change from run to run, you can, in the first run, you collect that information, save it somewhere, and then use that in the next run. Or you start your program, and after you have decided, and after you figure out who's communicating with whom, then you call these functions. But by then, you might have already got some data on each process that you might need to redistribute to match this new numbering that you're going to start using. Right? Yeah.
I was going to mention to ask whatever is generating the mesh, they can output a graph.
Right. Yeah. Yeah.
No, just a comment. So typically, what people do is the so-called Morton ordering, right? Mm-hmm. So you actually have a space filling curve that decides what is the optimum curve to actually communicate. And what we tend to do is actually we move the blocks such that they are following that curve. But what you are suggesting is basically the opposite. Just change the ordering of the ranks.
Yeah, change the number of the ranks. So there's no reason that whatever rank you get in COM world is the rank you have to continue using. You can get a different rank that is better suited for the communication pattern.
Because you could do the opposite, right? Take the data.
Yeah, but that require moving data is more expensive. This operation, you're not moving anything, so that's cheap, right? Yeah.
But you still move the data only once.
When?
At the beginning, for example, and then you just keep communicating. I'm saying you might move the data only in the first stage, and then you communicate.
Yeah, so this is needed where you're communicating throughout your program, and you want that communication to be fast, and so you want that communication to be among processes that are located somewhere nearby, whatever nearby means, or on the faster links or on the same node or whatever. So however you achieve that, if you can achieve it in what way. So not all codes follow the method you're suggesting. There are other types of decompositions where this might be. And I have an example on the next slide that shows something else. Yeah?
Maybe this is a ridiculous question, but how does MPI know what are the fastest communication routes?
Yeah, so that's the other problem is how do you map. So what the user is effectively specifying is a communication graph, which could be a simple graph like a Cartesian is, a 2D stencil code is a relatively simple communication graph. You could have a more complex graph. How do you map that graph onto the network topology of the machine? So that people have done some work on that, and there are some heuristics they follow. So it will try to do a good job for you. So that itself can be a research problem in the most complex, the mapping.
Is that determined at runtime?
That mapping is an algorithm which is run during one of these topology functions, and it gives you an output. Is it clear what I was saying? And I think I have an example on the next slide which might show this. So let's say this is the communication graph in an application where these are the ranks that are communicating, and the edge weights in some sense represent the amount of communication between these ranks. So what it shows is that 0 and 1 never communicate directly. 0 communicates with 3 and 5 and 6, and similarly 1 communicates with 2 and 4 and not with anyone else directly. So if you were doing a naive mapping, that is you just launched the job, your scheduler might just put 0 and 1 on node 0, then 2 and 3 on the next one, and then what's that? No, this should 4 and 5. This should be, and then 6 and 7. So that's the default mapping. But if you look at this graph and this mapping, it's not the best fit. So what's the example? Right? Yeah, 0 and 1 never communicate. So there's no point in putting them on the same node. And you'll find other examples like 4 and 5 never communicate, but the default mapping puts them on the same node. So that's not a good mapping. So what can be done is, at this point, if you call the MPI graph topology, the create function, what's it called, disk graph create, and there is a way of specifying this communication graph. If you call that, MPI could return a new communicator with this kind of mapping, where 0 and 3 are on the same node here, and 1 and 2, 4 and 7, and 5 and 6. And there could be other mappings that would also be reasonably good. This is just one example. So now you have 2 communicators. One is your default COM world, and this is the new one you get out of this function with a different mapping, which you can call your COM world if you want, and you can give it any name. It's a variable after all. And what has happened is nothing has changed. These processes have not been moved or migrated or anything. The same process has rank 1 in COM world. It now has rank 3 in this new communicator, and so on for all these other nodes. And now if these processes behave as if that is their rank, they ignore their COM world rank, they don't use COM world for any communication, they use this new rank for their communication, then this code should run more efficiently, because then the communication between 0 and 3 is among ranks on the same node and so forth. So is that clear what we're doing? Yeah.
So just to be clear, once you are done creating the
new communicator,
new communicator and the card created, then you actually go and read your data.
Yeah. Yeah, because that's a good point. So after you have done this, then you can read your data from disk. You read zeros data here and threes data here and fives data here, and then you can start computing and communicating. And the reason I say do it before, do this communicator creation before all the data is, if you had already read the data here, you would have one step of redistribution to get it in this form before you start communicating, and that costs you something. That might cost you more than anything else, more than is worth doing this stuff.
But how are you gonna, maybe follows that one, how are you gonna know if you didn't read the data that this is the optimus? Maybe
again, you could know that from your you could know it from the graph partitioner, from the way you're dividing your data.
I have another structure which just says how the
You could know it from a previous run. You have run it before, so you have profiled it. You know that this is the communication pattern. And in simpler cases, you can know it from your data distribution, from your by just looking at in a regular problem, you could just know it. In an irregular, it's more difficult. Yeah.
This might be sort of stupid, but this is sort of not really creating a load imbalance, but it'll highlight that problem more, because some nodes like 0 and 3, their communication will be done really fast compared to node 1 and 6 or something like that. And
right here?
Yes, for example, the communication between node 0, the process 0 and process 3 would be done really fast when the program is executing, because they are on the same node, compared to communication between process 0 and process 5, because they are on,
Yeah, but they're still in some sense nearest neighbors, so they can. It's not too bad. Yeah. So you're still left with the limitations of the system, that there is uneven communication. The speeds are not uniform. So if you had a system where it didn't matter, where the processes were, the network was so fast that it didn't matter. You could just be anywhere and you'll get the same performance. Then all this is not relevant. It becomes relevant where you have a non-uniformity, and that is the case. That cores on the same node are faster. Nearest neighbors in a torus are faster than going all the way across, particularly for short messages.
And so this can be thought of as reducing the bandwidth in a very loose sense, I would say, because this is sort of similar thing we are trying to do.
Yeah, you're reducing the bandwidth consumption in some way. So you're sending more data on the faster links than on the slower links. Yeah.
Yeah, I just want to clarify. We're talking about two different things here. The first is the MPI topology that you're creating, which is just for convenience. I mean, you could leave the numbering the same as before.
Yeah.
This is just so it's more convenient when you write the communication routines.
Yeah, well, there is a convenience factor also, but I haven't yet spoken about the convenience factor. Right now, I'm just talking about the performance factor, because
there is the performance factor of loading the data in different places, but you don't need to change the numbers of the ranks.
No, the performance is not the loading the data in different places. So the performance is these edges represent the communication graph and the frequency of communication or the amount of communication. So we have in this new ordering, the ones that communicate the most, say 5 and 6 are communicating heavily, so they are located on the same node here. Whereas here 5 and 6 are across nodes. So this is a performance optimization here, because now all the communicating pairs of processes are somewhat nearby, either on the same node or on nearby.
I think the catch is to do it before you load the data. So when you load the data, you load it in the optimum way.
Yeah, before you load any data, you have to create. Yeah.
The numbers could be the same between the two of them, but the data is in a different place.
The point is actually that the numbers haven't been renamed at this point. The numbers being renamed is the next step, where that's the convenience portion. As you can see on the chart, they've just been reordered for where they should live, referring the same number to where it was previously on the old graph.
I see now. Thank you.
So this is the performance, and the convenience part is that MPI provides functions for knowing who is your neighbor. So in a 2D mesh, you typically want to communicate with a north, south, east, west, and in 3D there'll be even neighbors here in the third dimension. And the send and receive functions require an explicit rank. They don't understand the 2D Cartesian topology or anything. So how do you know who's the rank in all these dimensions? So there are convenience functions for that. So you can say, give me my neighbor in the north direction, even 2 hops away, and or all those things are there. So that's the convenience. And even in the graph, you can query the graph to find out how many neighbors I have and who are they and this and that. So those are the convenience functions. So again, is this clear? Why are we doing this and how this is helping? Because the rest is more or less detailed, just how do we do this. So these process topologies have been there since day one in MPI, since MPI 1. MPI 1 defined 2 types of topologies, Cartesian topology, where you have any number of dimension mesh, 2D, 3D, 4, 5, whatever, that's a variable. And the other was a graph topology, where that's more general, where you actually specify the nodes and edges. But the MPI 1 way of specifying the graph has not a bug, but it has a problem in that it requires every process to specify the whole communication graph, not just its own part of the graph, but the whole communication graph of the whole of all processes. So that's a scalability problem. So let's say if you're running on a million process system and everyone's communicating with so many processes, each rank has to specify this whole communication graph. That's how much memory does that itself take to specify that graph? So because of that problem, to address that problem, MPI 2.2 added new functions where you can specify this graph in a distributed way, where you can specify just your own own neighbors, or there is a second way of doing it also, but you don't need to specify this whole graph and thereby consume all this memory just to call this function. And the other one is MPI 3 added collective communication functions that operate on in a neighborhood, where a neighborhood is defined by the process topology. So if you're doing stencil communication, nearest neighbor, you can just do an all gather defined on a communicator that has a Cartesian topology, and that will be restricted to an all gather among your nearest neighbors. So effectively, you can do this, the life code using a collective function. You don't need to do the sends and receives. The all gather will do that for you, and we'll see how that is done. Yeah.
Can you change the topology in the middle of the program?
You can create a new topology. So let's say you called a topology creation function on COM world. You get a new communicator, right? So if you want another one, you have to again start with COM world and get another one, and then you start using that one. And you can just ignore the previous one, because after all, they're just ranks they're just ranks, but logical ranks in some way. Okay. Yeah. So the first Cartesian the topology constructor function is the Cartesian topology, and it's simple because it's 2D or any D mesh type of thing. So what you do is you pass an input communicator, which could be COM world, it could be something else. The number of dimensions in this Cartesian topology, there is no limit. It can be any number. Let's say 2 or 3 would be common. Then this is an array where you specify the number of processes in each of those dimensions, 0, 1, 2, 3. That's why it's an array of ints. The other parameter is whether this is a periodic topology. That is, if you're on a 2D mesh, what is the upper neighbor of the topmost row? Is it nobody, or is it the last row? Is there a wraparound? Is it periodic? It's up to you to specify. So you could say yes or no, or true or false in this. So this is again an array to specify in each dimension, is there that wraparound there? And again, this is just for convenience, because sometime in your code, if you ask who is my neighbor at the top, this information is needed to say whether your neighbor is nobody, proc null, you don't have a neighbor, or your neighbor is the guy all the way at the bottom because of the wraparound. So that's that. The reorder parameter is, again, you indicate is, should the processes in the new communicator be reordered or not? Should they have a new rank or not? So typically, you would want to say yes, that is, go ahead and reorder, because by letting the implementation do that, you're letting it give you a new mapping where the performance feature comes into play. Suppose you said no to reorder, then all the ranks would have the same value in the old, same number in the old communicator and the new communicator. So you will lose much of that performance benefit. You will still get the convenience features. So the neighborhood functions, who's my neighbor, all that would still work. You will be able to use that part of it. And there might be some performance benefit in the sense that you have conveyed to MPI the communication pattern, that this is a 2D or 3D stencil code, so it's going to be nearest neighbor. So maybe it can batch the communication in some way. But I would recommend specifying the reorder as yes or true or whatever is the value it expects for 1. I think 1 means yes, to say go ahead and change the ranks so that you get a new rank in this new communicator such that the communicating processes are nearby. Yeah, so that's what all this says. Is this clear? It's a simple function. Yeah.
That means I can use this one to implement periodic boundary conditions on very large meshes, like if I have blocks in between and stuff like that.
It should be. All this says is it'll tell you who your next neighbor is, and if you say yes, it'll be the neighbor at the bottom of the grid, if that's what you mean by periodic boundary condition.
Well, yeah, like transfer data from this part
to
the bottom of the
that's what that is
bottom of the other one.
Yeah. Okay. So that is cart create. So this is just an example. So for let's say you have a 3D topology. So this is how you would do it. Your number of dimensions would be 3, and you pass the DIMS array where you let's say it's 5 by 5 by 5. It could be, that means you have 125 processes total. Yeah.
Am I right? There's actually functionality in MPI that can.
Yeah, that's my next slide. You're right. That's my next slide. You're saying periodic thing is 1, so yes, you're saying it's periodic, and this says don't reorder, but I don't. We should change that to reorder. That's a better example. But this is just an example, and the output of it is a new communicator. And from now on, you can start using the new communicator for your communication. So now the one question is, as he raised, is let's say you're running on some number of processes, 520, right? How do you know what is a good 3D decomposition of 520? X by Y by Z. How do you come up with this equivalent of 5 by 5 by 5? It may not be so easy. So MPI has a function that you can call that it will suggest something, and whether you want to use it or not is up to you. So what you specify is the number of nodes, and this is the number of processes. So the example I gave was 520. So you pass 520 here, and if you want a 3D decomposition of that, you pass 3 out here, and in this array, MPI will fill this array with a suggested decomposition that is good for 520. So forget 520. Let's say you have 30 processes, and it's a 2D mesh. So should you do it as a 6 by 5 or a 10 by 3 or what? You don't know. So MPI will suggest something, and unless you know better, no harm in going with the number suggested. Yeah.
What's the basis of the MPI suggestion?
It could be tied to the underlying network also. It could be tied to what works, what is a good fit for the underlying system. Or it might just try to maintain a balance, and instead of a 6 by 5 is a more, instead of having a 10 by 3 long and thin, it might. So there are some heuristics within MPI implementations for that, some algorithms.
And this might be something stupid, but what if the user says an odd number for a 2D graph?
Then you might get an error. These functions are are allowed to return error also, right? If you say 11 and you, then it might say 11 by 1 or something. You know, even that might, I don't know. It'll be specified. So if you look up this MPI dims create function in the MPI standard, that'll be specified what it does.
Yeah. Is there a way to include the grid dimensions in calculating this? Because if you have a domain that is really long, then you would prefer a 10 by 3 rather than a 5 by 6.
Yes, and there is a way to do that. Is that in this dims array, you can fill in some of the, pre-fill in some of the values. So let's say you know that one of your dimensions is long, you can fill in one of the values as some number, and it will fill the remaining for you, or something like that. You know? So there are some hints to give MPI suggestions in that regard. Or you can even totally ignore because this is just a suggestion. You don't have to follow what it replies. But typically what you do is you call this, and you feed the output of this to this function. So you just call that function and then feed that the dims that came here, you pass it to dims create. And that's in the next slide. Yeah, this slide does that. Yeah. So I've done MPI com size of com world, and then I call MPI dims create with this size 3, and then this is a dims array, and then I just pass the dims array to cart create. That's the more typical use of that function.
That makes the dims create on different machine, like make a different the array of the dims.
Yes, if you run it on different machines, you might get different answers for. But it won't change your code in any way. It might improve your performance, or it will try to return a value for that machine that might be good for that machine. Yeah?
So what does it do, the dims create? Does it really look at the hardware connection and like do some tests of data?
No, it won't test anything. It won't actually run anything. It'll just be based on knowledge that, let's say you're running on the blue gene, so it already knows that it is on a blue gene, and it already knows how jobs are assigned on the blue gene, what are the typical partitions like. So it will have an algorithm that takes those things into account right away. It won't run anything for you. And if you're using a generic implementation like MPage on a laptop, what it will do is it will try to make a most sensible choice. So it will try to make it more of a square than the thin rectangle. So if you do 30 and 2 dimensions, it will suggest 6 by 5 rather than the 10 by 3 type thing. Yeah.
When we compile the MPage on specific machine, does
it
like turn some parameters so that people, when they run the calculation, automatically like allocate these parameters?
Well, yeah, that could be done, but I don't think this function is that much optimized in the stock MPage that it would, when you install it somewhere, it will do something more special for this function. But typically, a vendor implementation of this function might be. So if you're running on a Cray or on an IBM, they might have done a more specific implementation of this function because they are running on specific hardware. Yeah.
So the DTQ has I think it's called the personality library, is that right? So they have that full 5D torus information.
Yeah. And they also have some mapping stuff that you can do at launch time where you can, that might be in the examples also. In that example folder, there is something called somebody pointed out during the break. The sample runs file, you'll see something it's called run mapping or some mapping, where you can specify the way the job is launched on the torus, whether it's launched first in this dimension and then in this, and A, B, C, D, and then whatever is the next name for that. So yeah, there are some, you can look up the ALCF documentation on mapping on the torus for this. Yeah, and even on the Sequoia, there similar stuff should be there. Okay, this should be clear. And right, so there are other convenience. So now it's all about convenience. You've already created this communicator. You're already using the new ranks, so your performance already should be better. So how can MPI help you just knowing who is what and who's your neighbor and so forth? So let's say you could be in a library and you don't know how many dimensions were there in the communicator because the user created the communicator. You didn't create it, so you don't know what the user did. So this just retrieves the information. What were the number of dimensions? Then you can get this actual size of the dimensions. So this is all what the input that was used to create the Cartesian topologies is returned in these functions. Then these cart rank and cart coords are, cart rank, it translates coordinates in the Cartesian topology to a rank. So, let's say you're in a 2D Cartesian topology, and then, from 0 to number of processes in this dimension and 0 to number of processes in this dimension. That's the 2D Cartesian coordinates. Who is 4, 4 in this 2D mesh? And what is the actual rank of that process? That can be, you can get using cart rank. And then the reverse of that, given a process rank, where does it lie in the 2D or 3D topology is given by this function, cart coords. So translate a rank into coords. Input is a rank, output is the coordinates in the Cartesian topology. So these are all the convenience functions. So if all this was not there, you would have had to figure it out somehow. You would have had to do the calculations, right? Because in your 2D stencil code, who is your right neighbor, who is your left neighbor, that somehow you need to figure out that. So these are the convenience things. And yeah, so the cart shift tells you who is your neighbor, because the first thing you want to do is I need to know my neighbor top, down, left, right, and sometimes in the third dimension also. So that is what cart shift does. It says, given this communicator, which has the Cartesian topology created for it, the direction is basically 0, 1, 2, 3, which dimension of the, is it in the 0 dimension of the topology or 1 or 2? And the displacement is, you can even find your neighbor 2 hops away. It's not just your nearest neighbor, or any number of hops away, basically. So the displacement could be 1, 2, 3, 4, whatever. So it's a substantial convenience function, because otherwise to calculate that means you have to know exactly who is located where. And you can find that not just for yourself, but for any rank. So for any ranks, you can find out who its neighbors are, right? So these are all convenience functions. And it can return proc null. What is proc null? Proc null in MPI is basically a null rank. If you do a send to proc null, nothing happens. The code won't fail or anything. It's just a null. So when will it return proc null is when you are at the top or the edge rows of a stencil and the boundary, and it's not periodic. So there is nobody to the right of you or nobody to the left of you. So that's that. So is that clear for Cartesian? Yeah.
Do we specify the direction somewhere, or is there something different?
Yeah. So this is the direction. So that tells you, whether it's 0, 1, which. Whether it's in this dimension or in the third dimension of the grid.
Yeah, we specify it somewhere, or
what do you mean? So this is where you specify it, right? This is where you pass that number to this parameter is where you specify that. So 0 means something, and if you actually look at the function, it will tell you what 0 means there and which one is 1 and which one is 2 and so forth.
So there is a difference.
Yeah. Okay, so that was Cartesian topologies. It's easy. You create the topology and you get a bunch of these convenience functions to know who is where. That you don't need to do any calculation. It tells you who is with the ranks and the coordinates. The next one is the graph topologies. This is the graph function from MPI 1, which I said, and you should not use it because there are other functions that are better. So I'm not going to even talk about this. And the reason for not using this, as I said, is you have to specify the whole graph at each process in your program. So it's not scalable. Not scalable in the memory sense. On a big system, you're consuming too much memory just to specify. So instead, use these MPI 2.2 functions for distributed graphs. Yeah. So there are 2 ways of doing this. One is called an adjacent graph, and the one is a more general way. So the first one is what is called dist graph create adjacent. And in this method, each process specifies who its neighbors are in this communication pattern. So you just specify your neighbor information, So that's why you're not specifying the whole graph now. It's simplified into just specifying yours. So it's memory efficient, and it has a whole bunch of parameters simply because you need to specify these things. So this is the old communicator, the in degree and out degree. So in a graph, you could have edges coming to you and edges going out of you. What that means is coming to you means you're receiving messages, and out means you're sending messages. So you can specify both out here, that I have neighbors to whom I am sending and neighbors from whom I'm receiving. And sometimes you could have a neighbor from whom you're sending and receiving, so that will be represented in both places. So the first few parameters are for the incoming edges, those who are sending to you. So in degree is the size of these remaining arrays. So this is the number of neighbors you have who are sending data to you. So this will give their actual ranks. This is the weight of each of these edges in the graph, and the weight in some sense represents the amount of communication. So it's not precisely defined what you should specify as the weight, but in some sense, the higher the weight means the greater the communication. And we might have an example on some of that. So that's for the sources. Similarly, the out degree is the number of outgoing edges, that is the number of neighbors you're sending data to. And this array will have the actual numbers, the ranks of those processes. And this is the weights for those edges of that graph. MPI info is another, we haven't looked at MPI info, but it's a way to pass hints to the MPI implementation. And it's used in other places. It's used in the I/O interface. It's used in dynamic processes. It's used in one-sided. I probably won't go into detail because it's a topic we didn't have time to cover, but you can look it up. There is information on how you can, for now, just ignore it. So a valid parameter here is MPI info null in all caps, which means I'm not going to bother with that now. That's for advanced performance tuning. So just pass this as a MPI info null. And again, the reorder parameter is should the ranks be reordered in the new communicator. So you typically want to say yes here. And then you get a new graph that has this topology embedded in it. So this new communicator knows about this graph topology. And again, along with it comes some convenience functions that we will see for knowing who your neighbors are and so forth. So that was the adjacent graph, and this is just an example that suppose this was the communication graph among processes, and it's a directed graph, so it has the send and receive information. Then rank 0 would have these parameters. The in degree is 0 because nobody is sending to rank 0. The out degree is 2. There are 2 edges, and the destinations are 3 and 1. And similarly for process 1, you could see that in degree is 3. There are 3 senders to it. There are 2 destinations, and these are the sources and these are the destinations. So it's just detail of how do you call the function and the parameters for that function. Okay, so that was the adjacent. So the function name is disk graph create adjacent because each process specifies its neighbors. There is a second way of doing it, which is more general, and it says that, it is called MPI disk graph create, and here it is general in the sense that any process can specify any part of the graph as long as together they specify the whole graph. So rank 0 could specify the connectivity of rank 10, say, or rank 10, 11, 12, any subset. There are no restrictions on this, as long as together they have specified the whole graph. So it's a very general way, and in some sense powerful, and in some sense a little bit of a hassle for the implementation because you have to somehow figure out now how this graph has been specified. Yeah, you had a question, or you just, no, okay. Yeah.
Like if you specify rank 0 specifies about 10, 11, and so on, but then rank 11 might also specify.
Yeah, I think no harm done. No harm done. As long as it's not conflicting. I mean, as long as they are consistent in what they specify, no harm done. And in the previous case, in this disk graph JSON, some information is specified twice, right? Because where is that? Here 0 is specifying 1 as its neighbor, and again 1 is also specifying 0 as its neighbor as a receiver and sender. So you're getting duplicate information in any case. Whereas in this one you don't need to specify the duplicate information. You just specify it once and that's enough. So this is more flexible and powerful and convenient. Yeah?
So in this one, it's possible for node 0 to specify part of the connectivity of node 0
Sure.
and node 10 to specify part of node 0's connectivity.
Yeah.
Okay.
Yeah. As long as together they have specified the whole thing, which part who specifies it doesn't matter.
How do you know that you specify everything?
Well, the user has to know that. The MPI will never know because it doesn't know what the real graph is, right? So if you don't specify something, you have specified an incomplete graph, and MPI will just go ahead with that. Your communication will be slightly different than what you had specified, so you won't get the full benefits of it. Yeah. Okay. So this again shows an example where you're using this disk graph create. So suppose this is the graph. Then I think in this example, if there's no mistake, rank 0 specifies this and rank, oh no. So this doesn't specify the whole thing. I was thinking that that's all that is needed, but that's not true. This is just showing that rank 0 is now showing what? It is showing it's showing the sources as 0 and 1, and the destinations as, so it is showing the connectivity information for ranks 0 and 1. Process 1 is showing the connectivity information for ranks 2 and 3, and so forth. This ... is meant to indicate that others will show the remaining. So you can show anything. It is somewhat random. It is just an example. Yeah. N is this thing which is effectively the size of these remaining arrays. So how many entries are going to be in these source, degrees, destinations, and weights arrays is this N. And it could be any number because it doesn't have to indicate anything completely, right? Because some other process might indicate the rest of it. So it is up to the user what that might be. Okay, so that was that. And now come the query function. So you have specified the graph, you got the new ordering. These are just the convenience functions. So what is this? Okay, so this is disk graph neighbors count. It returns the number of neighbors of the calling process. So if you call this, it will tell you how many neighbors you have and what are the weights and the in degree and the out degree, that is the sources, destinations, those kinds of things. Disk graph neighbors is the actual list of the rank. So this only tells you the number of your neighbors. This tells you exactly who the neighbors are, and so that's why it has these array outputs. So it will give you a list of ranks and so forth. Yeah. So those are the only two query functions for graphs. Then there is another function to know whether a given communicator has a topology assigned to it at all. So that's you call MPI topo test on a communicator, and then in the output you will get it is a graph, which is the old MPI1 graph, and that's why it has an UGS next to it. So that means don't use it. Is it a Cartesian? Is it the distributed graph? Or is it undefined? Undefined means no topology. So for example, you could call this function on MPI com world, and you should get the status as MPI undefined, because the com world doesn't have any topology, never has topology associated with it, right? Some other communicator. So this is, for a library, you might need to know. You pass it a communicator. The library might need to know, is there a topology associated with this communicator? So that's how you test for it. Is that clear? So this was basically topologies, and after that there is some slides. Bill, you're next for the stuff. So yeah.
So aside from using it for reordering, you don't typically use these directly?
Yeah, it's for the reordering for one and the convenience for the others. So even if you don't care for the reordering, let's say you're just running on your laptop, so the reordering will not matter. The convenience is useful. That like even in the MLife code, it uses cart create because you need to know who your neighbors are, and that can be a pain to calculate, particularly in 3D. This gives it to you directly.
Okay, I'm just thinking normally I would already know who my neighbors are. If I'm like running on a mesh, I would already.
Oh, yeah, on a mesh you would know, but if you're on a just a stencil thing, you don't know. Yeah.
MPI cart shift, will it give diagonally opposite processes?
No, I don't think it gives. It gives only in this dimension.
Normal to the faces or the edges.
Yeah, but you can ask for the left guy's right. Top neighbor or something. Yeah. You can find that way from your coordinates. The diagonal coordinates, and then get the rank for that. Yeah. Yeah.
Are there any routines in MPI that care about the weights you specify?
No. It's useful. It just indicates the amount or the frequency of communication. So in this graph topology function, it will look at the weights to know the amount or the intensity of the communication, and thereby know which need to be placed closer. So it's just an additional feature, the weights. Yeah.
This is probably problem and configuration dependent question, but based on your experience, what's the typical improvements have you observed?
Is that what you have in the next slide? Some improvements, those numbers? You have some graphs in?
Yeah, I do have some graphs that show what we have observed sometimes. It's very dependent on the implementation, the current state of, even the implementation on the same machine over time tends to change.